care chiar lucrează cu tehnologiile respective poate să vină cu niște chestii mult mai practice și cu niște situații concrete cu care cel mai probabil te vei întâlni și tu în realitate.
Eu personal de obicei punctez pe faptul că e foarte important să înveți cum să caute informația mai degrabă decât să fie învățată.
Cred că avem de învățat unii de la ceilalți și este un mod foarte eficient de a face asta.
Asta mi se pare fain că și eu la rândul meu am avut participanți la curs de acum vreo 2 ani care acum, de exemplu, activează ca voluntar în Agile Hub.
Agile Hub există atâta timp cât există oameni dornici să contribuie.
Celor care nu au auzit niciodată de Agile Hub, le-aș spune să vină la un curs.
Sunt Mihály Török, sau Miși, e mai simplu așa, și vă mulțumesc că ați venit la prezentarea Trimble. O să vorbim despre tehnologii de baze de date. Cum am spus, sunt Miși și sunt DBA în cadrul Trimble. Mă ocup de optimizare de baze de date, ceea ce mi-a plăcut de fiecare dată, din totdeauna mi-a plăcut să optimizez baze de date și să lucrez cu baze de date, să le dezvolt. Și ca atare, pe parcursul anilor, am mers tot mai aproape de baze de date. Despre această prezentare trebuie să vă spun că și noi vrem să vă vedem și fețele, este important pentru noi să vă vedem că e mai ușor să ne dăm seama dacă v-ați pierdut și să mai aprofundăm un pic. Dar dacă credeți că nu vreți să vă vedeți când puneți o întrebare pe canalul de YouTube după terminarea prezentării, atunci nu trebuie să porniți camera. Despre această prezentare, eu de fapt o să vă explic ceva din prezentare, o să vă explic mai mult despre prezentare și o să vă răspund la întrebări. Prezentarea e ținută de colegul meu, Joe Mastroianni. El este Distinguished Engineer și arhitect, e în Trimble, este din Canada și din cauza asta diferența de fus orar fiind mare, nu are prezentarea înregistrată și o să pornesc eu înregistrarea și o să-l mai opresc din când în când cu ceva explicații și atunci o să iau și întrebări. Deci dacă aveți întrebări, vă rog să-l adresați în pauzele dintre prezentare, pentru că în timpul rulării înregistrării nu o să ne auzim bine. Așa. O să mai fie și întrebări și răspunsuri și la final și o să avem și un mic concurs la sfârșit cu ceva premii. Să pornesc atunci și prezentarea. Așa. Cum am spus, este despre baze de date în Trimble și puteți învăța din această prezentare ce baze de date folosim noi și care au fost unele neajunsuri sau care sunt avantajele și dezavantajele baze de date. Dar să lăsăm atunci pe colegul meu să se prezinte și să vă prezinte prima parte a prezentării, după care o să mai vorbim, vă mai explic un pic mai pe internet.
Hello, everyone. My name is Joe Mastroianni. I am a systems architect and a distinguished engineer with Trimble. And today I'm here to discuss database directions, trends in database storage technologies, and some decision processes and experiences we've had over the past few years in Trimble around selecting data storage, use case specific data storage, and all kinds of things like that. Before we get into the presentation, I obviously want to express my appreciation at being asked to speak at this year's event. Thank you to my Trimble colleagues in Brașov for reaching out and asking me to talk about this topic, which of course I'm very passionate about. Thank you to Mihály for being there live with everyone to answer any questions and provide any additional information that I may miss. So thank you very much before we begin. So let's get over to the slides. So as we can see, we'll be discussing database technologies in Trimble. And before we get into specific technologies, specific technology decisions, and things like that, let's just look at where we are currently with regard to data storage in Trimble, and I think in the market in general. So Trimble, across our various divisions and various applications, use a wide variety of database technologies, at least in the MEP, mechanical, electrical, and plumbing division that I and my colleagues in Brașov work in, have a listing right here. So in the context of relational, kind of more traditional relational database systems, we have many databases living in Microsoft SQL Server and others in Postgres. Across other groups, there's certainly use of MySQL and a variety of other relational storage technologies. Over in the NoSQL world, we have very heavy usage of MongoDB and other usage of Microsoft Azure Cosmos DB. And then, of course, we also have our traditional blob storage, Amazon S3, Azure Blob, any other kind of just more traditional raw file storage options like that. So between all of these and one or two others that we'll look at through the rest of the presentation, obviously each of them have their own advantages, they have their own disadvantages, and each of them can be used, or at least most of them can be used as more of a general kind of data store. But really, I think the question we want to ask today is should they be used as a general data store? Because, if you look back at things historically, it used to be back before relational databases, you had a lot of denormalized storage. It took up a lot of disk space, used a lot of compute, and then we moved into sort of the relational times where splitting out data into different, forms, third normal form, things like that, reduced the repetition of data and saved on storage costs. And that tended to be because storage on physical hardware was very, very expensive and lots of things like that. And that's becoming less and less true these days. And again, traditionally, you would spend a lot of money on kind of big hardware to run large databases, and also a lot on hardware licensing and software licensing and all that. So say you landed with, okay, I have a very large database, I'm going to run this on Microsoft SQL Server or Oracle or something like that. You tended to use that data store as your primary data store, and you used it to store everything, even if that data store was not very well suited to holding the kinds of data you were putting into it, because that's sort of what you have. And at least in North America, we have a saying that, if the only tool you have is a hammer, then everything becomes a nail. So if you had this one tool in your tool belt because you spent all this money and investment on it, that's what you used to store, all of your data, whether it was good or not. So moving forward from sort of this traditional world where you would put all your data into one kind of data store as more of a general purpose data store, we really had to think about what the world was turning into with regard to things like cloud hosting, Amazon, Azure, Google Cloud, things like that, and the preponderance of additional data storage options and the flexibility of being in the cloud allowed us to not have to isolate all of our data on a couple of big servers. We could create many smaller data stores that had very different focused use cases. So to do this properly, we had to develop an overall data strategy. And this meant a couple of things. Firstly, as we see on the slides here, we had to be aware of our data. And I think a lot of organizations, especially organizations that are very focused on software development, don't always have a good idea of what their data and their data footprint looks like. You develop applications, you develop services, things like that, and the data tends to flow. I think that there was certainly a very strong tendency over the last little while with the evolution of web applications and things to have sort of these UI first, UI centric designs, which was really, really great. It allowed us to move faster. It allowed us to focus on user experience. But by designing from mockups, from the front end to the back end versus the back end to the front end, as was done a bit more traditionally, it tended to make the data that backed all of our applications and our services kind of an afterthought. So the data would serve the user interface versus the user interface being sort of an abstraction of the data. So being aware of our data, disconnected from what the user experience is, but being aware of our data kind of in and of itself as its own thing is a very important aspect of this strategy. Being aware of the dependencies of that data. So you would have potentially, a data model, a domain model, and figuring out what lives inside of a specific domain and what lives outside of that domain, and understanding what those dependencies and interfaces are. We also need to be aware of which pieces of data we are authorities on. So which data that we, do we own? Do we know the most about? Say, we're a car company. We know a lot about cars. Maybe we don't know as much about roads, things like that. There's trying to figure out what bits of data do we focus on as an organization and what data do we consume from outside. And then, all of that feeds into thinking of our data as a first-class citizen in our development processes, and then representing the data that we have decided we understand, we are aware of its dependencies, we know what pieces of data we are most authoritative on, and how do we represent that data in an appropriate way, in a scalable way, and in a way that is well suited to the structure and the uses of that data. So how do we accomplish this? So those first three, as we can see here, being aware of all of the aspects of our data, well, we cover those through domain and data modeling, so creating detailed domain workflow models and data models, and then also around data governance. What pieces of data are critical? What data types do they have? Who owns the definitions of those data, of those pieces of data, and what change processes do we have when the structure and representations of that data changes? So that's a whole set of talks, I'm sure, in and of itself. What we're going to be considering today is sort of these last 2 points, thinking of data as a first-class citizen during application development and representing it in an appropriate and scalable way. So how do we do these last two? We consider the data, during initial implementation, during architectural discussions, and during the making of the core decisions around a basic system architecture. And then also, it's very difficult to make informed decisions about data storage technologies if you're not aware of current trends in data storage technology.
Bun, deci până aici colegul meu a prezentat ce baze de date folosim în Trimble. În principiu folosim și baze de date relaționale și de tip document și pentru caching. Ceea ce e important este că trebuie să cunoaștem în fiecare aplicație ce în bază de date avem nevoie și această cunoaștere trebuie să fie încă de la începutul aplicației, pentru că avem nevoie de această informație ca să știm ce să implementăm. În cazul acesta trebuie să cunoaștem datele, trebuie să știm ce relații sunt între date și cum putem să alegem o bază de date care să fie potrivită pentru nevoile noastre.
Avem întrebări din partea voastră? Dacă nu, am eu o întrebare. Ok, haideți că încep eu atunci. Am o întrebare pentru că chiar de curând am făcut o mutare de la un tip de bază de date la altul pe motive inițiale de costuri și apoi am zis că de ce nu, dacă ne putem ajuta și de SQL, de ce să nu o facem. Și atunci o întrebare pentru Mihály ar fi cum decizi ce fel de bază vrei să folosești, adică cum ajungi la decizia aceasta? Le încerci pe toate, faci 2 luni de încercare pe bază de date, apoi pe cealaltă. Cum iei decizia între bază de date relaționale și cea de tip document?
Da, am înțeles întrebarea. E foarte bună întrebarea, chiar excelent. Fie continuare în prezentare, dar până atunci ideea e că trebuie să știm ce avem nevoie în aplicația respectivă și să știm, să cunoaștem datele noastre. Adică nu mai e cazul să folosim un tip de bază de date pentru orice, pentru că mai înainte foloseai o singură bază de date că aveai licență, dar acum poți să folosești mai multe baze de date, fiecare să plătești numai pentru cât folosești. Și atunci, de exemplu, dacă datele noastre au multe relații între ele, atunci nu o să folosim o bază de date de tip document, care de fapt nu are așa de multe relații sau se pot modela relații în acea bază de date, dar o să avem probleme la citirea lor și inclusiv la consistență. Dacă baza noastră de date conține informații care noi nu știm foarte bine ce formă o să aibă, ce structură, ce coloane au, adică ce atribute are informația noastră, atunci putem să mergem spre o bază de date de tip document, dar decizia asta nu trebuie să vină înainte să analizăm datele noastre. Pentru că de multe ori putem să ne grăbim și să zicem că da, nu știm exact cum o să apară datele, că o să vină cu diferite informații din diferite locuri și atunci mergem pe bază de date de tip document. Și după aceea ne dăm seama că avem relații între ele, ne dăm seama că de fapt știm cum arată datele noastre, numai că nu îl știam de la început. Deci de aici trebuie să avem mult să ne gândim foarte bine la baza noastră de date și la datele noastre încă de la începutul aplicației.
Mai am o întrebare.
Da?
Dacă tot ai zis că inițial poți să folosești un tip de bază de date și apoi cealaltă, este costisitor procesul acesta de a muta datele dintr-o bază de tip document într-una de tip relațional?
Da, este destul de costisitor, nu atât ca și cost în bani, decât în timp. Adică trebuie să implementezi mutarea datelor și, de obicei, nu atât mutarea datelor, cât și aplicația pentru a accesa baza de date. Pentru că se schimbă foarte multe în aplicație, în accesarea acestor date.
Bine, mulțumesc mult de tot. Pe partea de grup, din chat nu am mai găsit întrebări, așa că... uite, întreabă cineva dacă poți să vorbești puțin despre bazele de date distribuite.
De bazele de date distribuite, o bază de date de tip document este cea mai potrivită, nu cea relațională. Relațională nu se poate distribui așa de mult, dar hai să vedem asta mai degrabă după ce ascultăm și prezentarea colegului meu despre aceste tipuri de baze de date. Da?
Ok.
Mulțumesc.
Bine, mulțumim.
So let's get into an overview of these technologies. I'll go through a few. I believe it's 4 today. I'm sure there are more. There are many others. They can be sliced and diced in different ways. Some can be classified under, some people sort of think of the current world of data as being, SQL structured and NoSQL unstructured, and those are the two classes, and that's that. I'm going to go a little bit deeper than that, but I think it's certainly an interesting discussion about what the sort of high level buckets of data technology are. Again, this interpretation is one way to go about it, but there are certainly others. So let's start off with one that many of us are very, very familiar with, relational database management systems, or RDBMSs. These relational database management systems are really centered around structured table schemas. So like a table structure that has very strict schemas, relations between different tables in the schema are very strong. They have strong referential integrity. And this brings a lot of advantages. Relational database management systems are very mature. It's very easy to find very experienced people with years of experience in modeling relational systems and managing and maintaining relational systems and all of that. And of course, from a data perspective, data that you enter into a relational system is very, very strongly consistent. So unless there are basically errors in logic or application errors or hardware errors, you tend to not have data corruption through, the only way you tend to have data corruption is through poor design choices or things like that. The features of the technology are very focused on maintaining data consistencies. Now, there's certainly disadvantages to a relational system because of those tight schemas and that strong consistency. Schema changes to relational systems tend to require systems being taken offline. Maintenance tends to require those systems to be taken offline because as requests come into those systems, whether they're read requests or write requests, there is a strong possibility of data corruption and of extending out maintenance times and things like that. And also, these types of systems are not very well suited, at least traditionally, to more of a distributed storage mechanism. So some of the other technologies we'll look at are certainly more suited to that, but because of the strong requirement for consistency, it tends to be challenging to have horizontally scalable databases, relational databases. That's changing a little bit with the advent of technologies like Amazon Aurora and Microsoft SQL Azure DB. Those are more cloud-first implementations of relational systems. But if we're talking about more traditional, installed on server versions of these systems, they tend to not be quite as scalable as other ones we'll look at. So some examples of these technologies, again, some which we may be very familiar with if you've been in the industry for a while: Microsoft SQL Server, MySQL, Postgres SQL, and of course Oracle, the big daddy of a lot of these. Again, most of the providers are sort of pushing towards more cloud-first implementations. So if you start to dive into architectures of these newer systems, you'll see they're not just, SQL Server sitting on a VM that Microsoft manages. There's many different layers. They tend to be cloud-first systems that are architected very differently from a traditional relational database management system infrastructure, with kind of these legacy, if you will, or current implementation interfaces, so like a T-SQL interface, a PL/SQL interface, on top of them. So it's very interesting. So I'd say, relational systems are more of, the traditional approach, but there certainly is some advancement towards making these systems more cloud first and more scalable as well. That said, we can move into kind of some more recent types of storage. So an example here is kind of your more traditional representation of a NoSQL system, document storage. Document Store is built against a document model. So basically each of your records, if you will, is a separate and discrete document. And those documents can have a common schema, but it's not a requirement like it was in the relational systems. Each document can actually have a variable schema, and that is both one of the advantages and disadvantages of this kind of a system. So unlike the relational systems, where there were very strong controls, very strong referential integrity mechanisms, document storage is much looser. There's no strong controls of schema. There's no strong controls of referential integrity, and that allows systems to be very, very flexible, very, very scalable. It allows schema changes to be done inline. Most of the logic around your data layer will live in your application code, versus in a more relational system where you would load a lot of application logic into the data layer, so into things like stored procedures and triggers and all of the tools that are available like that. This is more of a, shall I say, developer first kind of an approach where the vast majority of your application logic lives in your business layer. So again, really, really great because you don't have to sort of offload things to database developers, database administrators. You can do it right in your, for example, C# or Java code, which is great, but it also brings us to some disadvantages where sort of that same flexibility that allows developers to do all of this stuff also means that the developers have to do all this stuff. So schema references all of the logic that would in another system live in the database and stop you from causing data to become orphaned or invalid or corrupt lies with the development teams. So that really means that as a development team or as an owner of a service or an application, that service or that application needs to know everything about its data. It needs to know all the business rules, all the restrictions, all the relations, and all the dependencies in that data to represent it in a document format. Because document storage and sort of these NoSQL approaches in general are still fairly young in their life cycles, there's a tendency for people who don't have experience with them to come to them and say, this is great. Document storage allows us to do anything. We don't need schema. We can do whatever we want. But what you tend to do, if your experience tends to be in more of a relational space, is you tend to build sort of relational patterns into a non-relational structure, which ends up with a lot of sort of schema anti-patterns, which, you know, out of the gate may work because systems aren't under heavy load, but once systems start to grow, these anti-patterns start to create major performance bottlenecks. And basically, you know, if you start to build out a document store in a non-relational way, or in a relational way, excuse me, that is building in technical debt right up front. So an advantage to these systems is that, unlike SQL, these out of the gate can be very horizontally scalable through data partitioning and things like that. Now, one of the challenges that brings is that if you have many distributed nodes of data, you have to be okay with that data being eventually consistent. So if you have nodes in many different regions, you make a data update and it pushes those updates out to various nodes. Users or requests that come into those secondary nodes may still pull old, stale data. So your system has to be, either your workflow has to support the capacity to do that. So, you know, this might not be a way I would build you know, a banking application where it needs to be very up to date on, you know, account balances and transaction records and things like that. But in another system where if one request pulls data that is not entirely current, and that's okay, that may not be a problem. It all really depends on what the requirements of your use cases are. So examples of document stores are things like MongoDB, Cosmos DB, and Amazon, I believe in the last year, released a system called Document DB, which is also a document store. Document stores tend to be JSON based, so that's something that we're all very familiar with now. So it makes things, you know, fairly readable and things like that. So that's document stores, very, very flexible, really great way to represent data that can be encapsulated in sort of like a single structure.
Bun, așadar, despre baze de date relaționale și baze de date de tip document, așa cum am spus, nu, sunt diferențe suficiente. Unele baze de date relaționale mai mult axat pe relații, cel de tip document în cazul în care nu ai o schemă așa bine definită, dar este foarte ușor să ai și probleme de performanță în cazul în care implementezi niște anti-pattern-uri în bază de tip document. Revenind la baze de date distribuite, cele de tip document se pretează mai mult pentru că foarte ușor, de exemplu, Cosmos DB sau MongoDB se pot distribui pe mai multe sharduri și, de fapt, se multiplică puterea de calcul a bazei de date. Cele relaționale, un pic mai greu se pot distribui, ele sunt scalabile prin adăugarea de procesor sau de hardware, dar pe partea de Azure, adică sau Amazon, adică în cloud se pot scala, dar nu neapărat distribui. Dacă nu mai sunt alte întrebări, atunci putem să mergem mai departe la celelalte baze de date.
Este o întrebare de la Radu. Ce au diferit RDBMS-urile Cloud First față de cele tradiționale?
În principiu nu sunt, deci bazele de date relaționale care sunt Cloud First, adică special dezvoltate pentru cloud, ca și structură, ca și comenzi, nu au nimic diferit față de cele tradiționale, doar că suportul este diferit. Ele sunt puse pe servere în cloud și îl poți scala foarte ușor în timp ce lucrează. Nu sunt cele care sunt pe un calculator, pe un server local, nu poți să adaugi un procesor la calculatorul ăla dacă nu l-ai oprit. Dar în cloud poți să le scalezi, să adaugi procesor sau ce mai ai în memorie în timp real. Da, mai mult pe resurse, da. Bun, să vedem și celelalte tipuri de baze de date pe care le mai folosim.
Next up, we have a key store. Now, key stores are data stores that use traditionally a single key to seek on data. Now, if a data set is small enough to be stored in memory, or a server has enough memory to store a data set, this sort of key store mechanism can be really ideal for caching. Advantages of key stores are that they are highly, very incredibly performant, especially if they're in memory for seek type operations. They can have very strong built-in features for data life cycles. So, storing things like session data inside of a key store can be really great because that will have built-in mechanisms for expiring data and making sessions invalid and other things like that. Disadvantages of key stores, especially if you're going for sort of the in-memory cache kind of use case, is that they can be very expensive, and that because you have that one key field of data that attaches to another set of data of any type, whether it's structured, unstructured, external, etc., is that they're really not very flexible for searching outside of that key field. So you really do have to have your use case very narrowed in, where you say, this is the key that I need to search for all the time. So again, session storage, is very ideal. Or if you have sort of something kind of like user caching or something where there's a very consistent key that will always be seeked on, that's really the best way to go about doing that. So examples of key stores are things like Redis Cache, Memcached, Amazon Elasticache, many others. But really, as you can see, caching is really sort of an ideal use case for this. Next up, we have the graph database. Now, graph data represents it still represents objects, like you would represent in a document store or in a relational database, but it also has a very strong focus on representing relations between data. So what that really means is, you would pull in a graph database when the relationships between data are sort of more in the forefront than the data objects themselves. An example within Trimble could be vehicle tracking. So you may care about a specific vehicle on jobs, like say a delivery truck that's driving around making deliveries. But what you really care about more than that vehicle, that vehicle will be represented as an object. It will have a set of properties and all of that. But what you really care about with regard to that vehicle is not the vehicle itself, but all the things that are associated to that vehicle. So that vehicle will have a driver, and that driver has its own record. And that vehicle will have, as an example, a set of packages that it needs delivered. And there will be pathing between those, the delivery locations of those packages. So it's not so much the specific object and the set of data below that object. It's more that object and all of the activities and data and relationships of other things to that object that are important. So as we said, with advantages, really ideal for representing dependencies, data ownership, things like that. And relations, unlike in a relational database system, which you would think would also have relations as at sort of its forefront, here, in those in a relational system, you'll have relations in the context of foreign keys. They could be one-to-one, many-to-one, etc. But those relations themselves don't really have a lot of properties. Whereas here, the relations are also objects and also have properties. So, you know, a package in relation to a vehicle may have, you know, a property about what priority it is delivered in. That delivery, which the relation might be representing, can have obviously addresses and metadata around them and priorities and you know, things like that. So not only are the objects in a graph database, you know, full objects with attributes and things like that, but the relations are also the same priority and have the same complexity to them. Disadvantages around a graph database are that if you have a very large graph and you need to traverse that entire graph, so say, you know, you're trying to pull many vehicles from many countries or many packages from many disparate deliveries or something to that effect, traversing that graph can be quite slow. And graph databases are also not really great at ingesting very large volumes of transactions, because in a lot of graphs, the kind of the knock-on effect or the waterfall effect from making changes to elements in the graph can spiderweb out to many nodes in the graph and many edges in the graph and cause a lot of work to be done with each update. So really you want to have your graphs be relatively tight and relatively focused. Examples of graph databases are Neo4j, Cassandra, and surprisingly, I know I brought it back over here, Cosmos DB. Cosmos DB also has a graph interface. So you know, it's a document store. It can also be a graph. There's also a graph implementation of Cosmos DB. Finally, we have blob storage. Now, a lot of people don't really consider, when you're considering databases, if you want to call a lot of these more kind of more complex storage technologies databases, most people don't consider blob storage a database, but really it is. I mean, it's data storage in the context of being able to store, retrieve, read, you know, perform CRUD operations on data, which all of these other database types are as well. Blob just tends to be, shall we say, a little bit more straightforward. So data in a blob is stored as exactly that, a blob. It's stored as unstructured text or binary data. This is really the best option for your basic, robust file storage. So if you have a system that you are migrating into the cloud, and it has a large file server that has replication and backup and all of this stuff, one of the easiest things to do to gain some benefit of migrating you know, legacy on-prem systems into the cloud is to convert that raw file storage into blob storage. Why? Well, there's a couple of big advantages to blob storage. The first one being that blob storage is very inexpensive, you know, pennies per gigabyte of storage per month. It's also very, very flexible, very, very robust. I can't remember if it's Amazon S3 or Azure Blob storage that has something like 11 nines of durability. Effectively, I think, you know, at least a few years ago, Amazon had a claim that they have never lost a file in blob storage. At times they have been inaccessible, but there has never been data loss in blob storage. Out of the box, it's very distributed. There tends to not be like regionality to it. There tends to be deliverability layers that can be put in front of it, like content distribution networks, whether it's cloud native ones or something like Cloudflare. And again, very, very, very robust. So, you know, if you need raw file storage, blob is a very, very cost-effective, very, very easy to implement choice. Now, that said, blob is not quite as useful out of the box, shall we say, as some of the other storage technologies we went over. Blob storage, outside of some kind of very early, experimental efforts, doesn't really have a robust query structure. They tend to have APIs. You can do searching within specific buckets or containers. You can search on storage keys, so things like file names, but it's much more difficult. There's no robust standard query structure like there would be in something like a relational system with a very standard SQL interface, or even any of the other kind of more programmatically driven data stores, where there's, again, it may be proprietary, but there's a very structured way to get data out of those stores. With Blob, again, you can it's very easy to seek on file names, much like in a file system. But if you start searching through blobs, that tends to not be a very effective and performant use of compute resources, shall we say. It tends to be that blob files are searchable and linkable through other data stores. You may have file path stored in a relational database or something like that. And then really API-wise into blobs, there tends to be much more basic API capabilities. So basically the ability to create files, to read files, to update files. But what update files likely means is overwriting files, and then to delete files. There'll be more around like data access and rights management and things like that. But this is really, in the context of our data stores, the one that most resembles a file system versus sort of a structured, searchable set of data. Examples of blob storage are, of course, Amazon S3, Azure Blob, many others. Dropbox is sort of a blob storage. Box.net is blob storage, but really the big guys are Amazon and Azure and Google on Blob Store. So, how do we modify our processes and our application development to take advantage of these sort of very disparate data storage technologies? Well, the first way would be, if there are data storage specialists, be they database developers, database administrators, data architects, things like that, reach out to those people in your organizations to see what their thoughts are on how processes and things can be modified to take advantage of a more, I think the term would be polyglot data storage strategy. So instead of having, again, your files on a file server and all of your structured data inside a SQL database, looking at the different aspects of your data and saying, well, we see we're storing a lot of, files inside of a database, as an example, pulling those out into Blob, or we tend to have like, hey, here's a really great use case where, maybe our user records can be encapsulated into single documents, and maybe we can pull those out, or maybe there's places where we want data to be a little bit less normalized. And again, that might be a great place to implement NoSQL. So really, when we're designing new services, whether it's in the context of migrating existing workloads up into the cloud, or tearing, decomposing monolithic apps into microservices, there should really never be the consideration that we have a default data store. So whenever we're designing a new service, it goes into SQL. There should always be a consideration of what the data that you're working with looks like, how it's going to be queried, how it's going to be used, how it's going to be updated, and that will inform our decision at the time services are being created as to what their backing data store will be. Now, that isn't to say that you need to use a different data store for every service all the time. An organization can have a set of preferred technologies. So, in the context of each of these data types we looked at, maybe an organization prefers Postgres for relational systems. It prefers, Redis for key stores. It prefers MongoDB for document storage, and, it prefers Azure Blob for blob storage. So, there can be a sub list of technologies, but I certainly wouldn't restrict things. It's important to stay up to things and stay up to new features and different technologies and all of that. In addition to sort of this greenfield net new development, time should be taken ideally to go through existing services, existing applications, in the context of modernization, and seeing, hey, does it make sense from a cost perspective, from a time perspective, from a functionality perspective, to maybe rethink the data stores that are backing these existing services as well. And of course, very important for everyone in the organization, not just data specialists, to keep up, at least from a high level, on different data storage technologies, especially if your role is more, of an application architect, if you're considering things more out of the gate, at the beginning of a development project. Certainly very beneficial to take the time to keep up on things and, attend the conferences, read the documentation, go to the different trainings, and get an understanding of what these different technologies are, how they work, why they work, where they're best used, and, understanding that there's specific use cases or general use cases where different technologies can be beneficial. So that's all I have for today. If you guys have been asking questions throughout, certainly great, but now there's also some time, Mihály, if you want to field those, to take any questions that have been held till now. And I will also take this time to thank you all for taking the time to listen, and hopefully you gathered some good information from this presentation. Thank you very much, and I hope the rest of the event is really great and really informative. Thank you.
Nu te auzi încă, Miși. Ești pus pe...
Hello, everyone. My name is Joe Mastroianni. I am a systems...
Ok. Avem o întrebare din public. Trebuie să dai unmute, Miși, ca să putem să te auzim.
Da. Bun, deci am mai auzit despre key store, despre baze de date de tip graph și blob storage.
Ca un
Da?
spaghettified monolith cu data storage.
N-am înțeles.
Există o întrebare pe chat.
Da.
Legată de faptul că propunerea de graf DB se pretează mai mult la reporting decât la applications.
Acum, bazele de date de tip graf se pretează mai mult atunci când relațiile dintre entități sunt mai importante decât entitățile în sine. Nu știu dacă asta reprezintă de reporting system. Deci, de exemplu, social media este poate beneficia foarte ușor de baze de date de tip graph. Au nevoie de relații și de atribute pe relații dintre entități. De exemplu, cine e prieten cu cine, cine a dat like la postarea celuilalt și ce fel de like e respectiva postare. Asta e avantajul bazelor de date de tip graph. Dacă mai sunt alte întrebări?
Salut, Miși. Am eu o întrebare foarte scurtă. Ai povestit de scalarea bazelor date relaționale, dar aș vrea să te întreb care este statusul sau cât de mult ajută scalarea folosind replici de read-write, cel puțin în zona de cloud.
Pentru baze de date relaționale, replicile de read-write nu sunt tranzacțional sincronizate. Deci ceea ce se întâmplă în cazul acela e că acea replică care nu este masterul, da? Deci cel care este copia, el sigur nu o să fie sincronizat tranzacțional cu replica principală și ajută pentru că, de exemplu, poți să-l distribui pe mai multe zone de pe glob. Dar trebuie să te asiguri că dacă ai ceva date nesincronizate încă, nu îți strică aplicația. Deci asta este dezavantajul celor replicate.
Mulțumesc!
Mulțumesc și eu!
Mai avem în chat un comentariu care spune că un exemplu bun pentru graf DB pot fi articolele. Pe un articol pot fi implicate mai multe entități și legătura ar putea să aibă informația de legătură entități cu articolul respectiv. E autor menționat, e aprobat și mai departe.
Da, este un exemplu bun pentru baze de date de tip graf. No. Atâta timp cât rămânem la nivelul ăsta de relații, că dacă intrăm mai mult în adâncime pe zona relațională, atunci nu o să mai... s-ar putea să ajungă și o bază de date relațională bună într-o anumită parte a aplicației.
Ok.
Bun. Păi... avem și un mic concurs, ziceam la început. Puteți câștiga, 2 câștigători avem pentru câte o lampă Trimble. Dacă intrați pe Menti, da, și folosiți codul de pe ecran, 79 36 62 8. Da? Trebuie să vă conectați cu numele vostru, vă rog să folosiți numele din prezentare ca să vă putem identifica.
Bun. Până se conectează lumea, mai era o întrebare pe chat venită de la Radu, care te întreabă dacă recomanzi vreun tool.
Un tool de schema change fără downtime în MySQL. În MySQL nu prea știu dacă există un tool. În Microsoft SQL știu sigur că există proiectul de bază de date. Dar în MySQL până la urmă sunt scripturi. Deci se pot face scripturi care se pot rula și chiar și în high traffic, în cazul în care nu sunt cine știe ce mari modificări în structura bazei de date.
Ok. Mulțumim.
Bun, deci putem... Mulțumesc și eu. Mai e cineva?
Deocamdată o secundă. Nu am mai întrebat nimeni nimic. Am pus și în chat linkul și codul. Vă rog frumos să intrați. Tu ne poți zice, Miși, dacă sunt oameni.
Da, sunt.
Da, sunt 13. Teoretic sunt în jur de 20, poate nu vrea toată lumea să răspundă, să participe la concursul acesta. Așa că haide să-i dăm bătaie și să vedem.
Încercăm. Da, prima întrebare.
Felicitări celor care au răspuns corect.
Da, felicitări și să vedem și cine a fost cel mai rapid după prima întrebare. O să vedem și după a doua întrebare și primii doi primesc cadou.
Perfect. Haideți să mergem și la a doua. Felicitări, Andrei. Doar numele lui l-am reținut, al doilea nu știu cine era. Cer scuze.
Felicitări! Ia să vedem și cine sunt câștigătorii.
Ok. Bravo!
Bravo, Mădălin, și bravo, Robert! Vă rog să vă trimit pe chat o adresă de mail, vă rog să-mi dați datele de contact ca să știm unde să trimitem cadou. Să vedem Mădălin.
Mădălin și Robert. Sau pot ei să-ți lase ție adresa de e-mail dacă ți este mai ușor așa.
Da. L-am și trimis.
Perfect atunci. Felicitări încă o dată.
Felicitări și bun. Mai departe, mulțumesc pentru participare. Dacă mai aveți vreo întrebare așa pe final, știu că deja... Dacă nu, mulțumesc pentru participare și vă aștept și la prezentările de...
Și feedback-ul, te rog frumos să pui și slide-ul cu feedback-ul, da. Dacă puteți, vă rugăm frumos să ne dați feedback-ul acum, acum când aveți informația proaspătă, deoarece este foarte important pentru noi, astfel încât data viitoare să îmbunătățim dacă a fost ceva care putea fi îmbunătățit.
Da, vă rog să dați feedback. Este anonim și ne ajută ca să știm ce trebuie să îmbunătățim.
Dacă mai sunt întrebări sau dacă mai aveți ceva să ne spuneți, puteți să faceți acum. Dacă nu, o să-i mulțumim lui Miși și lui Joe pentru prezentare și pentru premii și vă invităm pe restul în main room, în linkul de dimineață, pentru a discuta un pic pe partea de cyber security și puțin legat de testare. Vor fi niște lunch and learn sessions pentru cei care sunt interesați de așa ceva.
Da. Mulțumesc și eu și dacă vă interesează bazele de date, după masă am și o prezentare de bază de date, vă aștept și acolo.
Ok. Mulțumim mult de tot. O zi bună să aveți. La revedere!
La revedere!